an algorithm that addresses all possible NM user item combinations in a linear running time by exploiting the algebraic structure of the variables. 5. Explaining recommendations. It is well accepted 10 that a good recommendation should be accompanied with an explanation, which is a short description to why a specific product was recommended to the user. This helps in
It is well accepted that a good recommendation should be accompanied with an explanation. What does that mean? If your recommendation is good, you don't need explanation. If you did a bad recommendation, it's when you need an explanation. If it is good, it is good. What do you mean? Which is a short description to why a specific product was recommended to the user. This helps in improving the user's trust in the system and their ability to put recommendations in right perspectives. Trust matters a lot. So if it is for trust, I say yeah.
Improving the user's trust in the system and their ability to put recommendations in the right perspective. In addition, it is an invaluable means for debugging the system and tracking down the source of unexpected behavior. Providing explanations with neighborhood-based, or memory-based, techniques is straightforward, as recommendations are directly inferred from past users' behavior. However, for latent factor models, explanations become trickier, as all past user actions are abstracted via the user factors, thereby blocking a direct relation between past user actions and the output recommendations. Interestingly, our alternating least squares model.
What did he say? In addition, it is an invaluable means for debugging the system, that's good, and tracking down the source of unexpected behavior. Where is it? Okay. Providing explanations with neighborhood-based or memory-based technique is straightforward. An explanation with neighborhood-based. As recommended, what does memory-based? Okay, neighborhood-based. Okay. Neighborhood-based. What is neighborhood-based? Neighborhood-based means that we know as a user, for example, you have used these products and we want to know if you are interested in this new product. So we estimate your preference in this new product based on your previous products. Or we can say, okay, other users like this product and you look like these users, so probably you will like this product. Or memory based is that based on your past behavior, which is like you like other products, and then neighborhood means you and other users probably. Is straightforward as recommendations are directly inferred from past users' behavior. However, for latent factor models, what is latent factor model? We say that a user's confidence or preference or R is a inner product of, like, we assign to each user a XU and to each product a YI, and then the R is just their inner product. That's a big assumption, right? However, for that is latent factor models. Explanation becomes trickier as all past user actions, we didn't have any actions here, are abstracted via the user factors, thereby blocking a direct relation between past user actions and the output recommendation. I didn't get this part. I think it says, when we do the latent factor, as I said, we just assume that each user has an XU. So, and his interest in the product item I is just related to XU times YI. And how is this YI related to other YJs maybe a bit more indirect, but the thing is that we find yi probably estimating through yj's, I guess. I don't know.
Enables a novel way to Interestingly, our alternating least squares model enables a novel way to compute explanations. The key is replacing the user factors by using EQ for
XU is user factors.
Equals YTCUY plus lambda I, 1 YT cup, U. Thus, the predicted preference of user U for item I, PUI equals YTI SU, becomes YTI, YTCUY plus lambda I, 1 YT cup, U. This expression can be simplified by introducing some new notation. Let us denote the F times F matrix, YTCUY plus lambda I, 1 as WU, which should be considered as a weighting matrix associated with user U. Accordingly, the weighted similarity between items I and J from US viewpoint is denoted by SUI equals YTI, which, using this new notation, the predicted preference of U for
similarity metric between item I and J, right? And it has YIWU. What is W? I don't know, but YJ. Then we want to predict the preference for use item I using this other edge.
Item I is rewritten as PUI equals X SUI ka J. J ra J 0. 7. This reduces our latent factor model into a linear model that predicts preferences as a linear function of past actions, ra J 0, weighted by item similarity. Each past action receives a separate term informing the predicted PUI, and thus we can isolate its unique contribution. The actions associated with the highest contribution are identified as the major explanation behind the recommendation. In addition, we can further break the contribution of each individual past action into two separate sources: the significance of the relation to user U, Kj, and the similarity to target item I, SUI. This shares much resemblance with item-oriented neighborhood models. In addition, we can further...
Okay, let's say this reduces our latent factor model into a linear model that predicts preferences as a linear function of past actions. Okay, yeah, RUJ. We know RUJs and we can compute RUI. This is the whole shit. Weighted by item similarity. Perfect. Each past action receives a separate term informing the predicted PUI hat, and thus we can isolate its unique. Yes, okay. The actions associated. The actions associated with the highest contribution, like having the biggest Sij, are identified as and then we pick K of them, right? Are identified as the major explanation behind the recommendation. Okay. They are the major one. In addition, so if user asks, why did you just recommended this to me? We say, oh, you like these K videos and they're pretty similar to this, so we thought you like it. This is good once you want to exploit users' preference, right? What if you want to introduce some new genres of movie or music to the user? And it should happen, because sometimes users do not know what kind of movies they like, and then they watch a new movie and they say, oh, actually I like this movie. So that may be a bit riskier, because there are a lot of movies that are in new genre and probably users don't like to watch them. Okay. But this model works better for Spotify or Netflix or YouTube. I don't think it works as well for Amazon. In addition, we can further break the contribution. Well, for product suggestion for sure. We can further break the contribution of each individual past action into two separate sources. The significance of their relation to user U minus CUIJ. What is CUIJ? Was the confidence of user U in J, which is similar to RUIJ. And what is U? U is bullshit. U is name of the user. And the similarity to target item. Oh, it's a UCIJ, it's a pair. Okay. ISIJU. This shares much resemblance with item-oriented neighborhood models, which enables the desired ability to explain computed predictions. If we further adopt this viewpoint, we can consider our model as a powerful preprocessor for a neighborhood-based method where item similarities are learned through a principal optimization process. In addition, similarities between items become dependent on the specific user in question, reflecting the fact that different users do not completely agree on which items are similar. What? I didn't understand this sentence. In addition, similarities between items like INJ, SIJ, become dependent on the specific user in question. So SIJ depends on you, the user, reflecting the fact that different users do not completely agree on which items are similar. That is true. So that's why they're talking about the I and SIJU and U and CUIJ. Okay. Let's get to the experimental study. I'm excited for that. This is the interesting part. This is the part that we prove our shit. And then we have a discussion. That's such a good paper. It's a good paper. Small paper. You should not say too much shit in your papers. Giving explanation through 7 involves solving a linear system YTCU y followed by matrix vector product. You can be done in time OF2 and mu plus F3 assuming that YTY is free. Actually, I want to tell Monzer how can we let's aim for a conference. Like the paper Diego sent. Yeah, dude, this is 10 pages. The previous favorite paper was 20 pages. Let's make it as short as possible. Experimental study. Go ahead, brother.
6. Experimental study. Data description or analysis is based on data from a digital television service. We were able to collect data on about 300,000 set-top boxes. All data was collected in accordance with appropriate end-user agreements and privacy policies. The analysis was done with data that was aggregated and/or fully anonymized. No personally identifiable information was collected in connection with this research.
All right.
We collected all channel tune events for these users, indicating the channel the set-top box was tuned into, and a timestamp. There are approximately 17,000 unique programs which aired during a 4-week period. The training data contains RUI values, for each user U and program I, which represent how many times user U watched program I. Related is the number of minutes that a given show was watched. For all of our analysis we focus on show length based units. Notice that RUI is a real value, as users may watch parts of shows. After aggregating multiple watches of the same program, the number of non-zero RUI values is about 32 million. In addition, we use a similarly constructed test set, which is based on all channel tune events during the single week following a 4-week training period. Our system is trained using the recent 4 weeks of data.
This paper is explaining how they gathered their data. It's interesting.
In order to generate predictions of what users will watch in the ensuing week. The training period of 4 weeks is chosen based on an experimental study which showed that a shorter period tends to deteriorate the prediction results, while a longer period does not add much value. Since television schedules change seasonally, long training periods do not necessarily have an advantage, even though we found that our core model is robust enough to avoid being contaminated by the seasonality. The observations in the test set are denoted by RUI, distinguished with a superscript T. One characteristic of television watching is the tendency to repetitively watch the same programs every week. It is much more valuable to a user to be recommended programs that she has not watched recently, or that she is not aware of. Thus, in our default setting, for each user we remove the easy predictions from the test set corresponding to the shows that had been watched by that user during the training period. To make the test set even more accurate, we toggle to 0 all entries with RTUI. This leaves us with about 2 million non-zero RTUI values in the test set. The tendency to watch the same programs repeatedly also makes RUI vary significantly over a large range. While there are a lot of viewing events close to 0, channel flipping, 1, 2 or 3, watching a film or a couple of episodes of a series, there are also some viewing events that accumulate to hundreds, have the DVR recording the same program for many hours per day over a period of 4 weeks. Therefore we employ the log scaling scheme, 6, with O equals 10A. 1.
What is 6? Oh, okay. The relation between R and C, okay. And he's talking about what are the parameters of the problem.
Other important adjustment is needed. We observe many cases where a single channel is watched for many hours. It is likely that the initial show that was tuned into is of interest to the viewer, while the subsequent shows are of decreasing interest. The television might simply have been left on while the viewer does something else, or sleeps. We call this a momentum effect, and programs watched due to momentum are less expected to reflect real preference. To overcome this effect, we downweight the second and subsequent shows after a channel tuning event. More specifically, for the TTH show after a channel tune, we assign it a weighting 1 plus E at B. Experimentally we found A equals 2 and E at B. B equals 6 to work well and is intuitive. The third show after the channel tune gets its RUI value halved. By the fifth show without a channel change, RUI is reduced by 99%.
Well, that's fucked up. Maybe they like the third show. So, look, that's the beauty of their research. They're being assumptive. Yeah, if you are watching the third show, it has a low RUI. That's it. We assume that. Fuck you. Somebody may say, oh, what about maybe I don't like the middle one, I like the third one. Well, good luck. Go write your fucking paper.
Evaluation methodology. We evaluate a scenario where we generate for each user an ordered list of the shows, sorted from the one predicted to be most preferred till the least preferred one. Then, we present a prefix of the list to the user as the recommended shows. It is important to realize that we do not have a reliable feedback regarding which programs are unloved, as not watching a program can stem from multiple different reasons.
Exactly.
In addition, we are currently unable to track user reactions to our recommendations. Thus, precision-based metrics are not very appropriate, as they require knowing which programs are undesired to a user.
Should join a program.
However, watching a program is an indication of liking it, making recall-oriented measures applicable. We denote by rank UI the percentile ranking of program I within the ordered list of all programs prepared for user U. This way, rank UI equals 0% would mean that program I is predicted.
We denote by rank UI the percentile ranking of program I within the ordered list of all programs prepared for user U. So each user U has a ranking for themselves, and product I has a rank in that rank. This way, rank UI is 0%. Why should it be in percent? Would mean that the program I is predicted to be the most desirable. It means the top of the list for user I, thus preceding all other programs in the list. On the other hand, rank UI 100% is end of the list, indicates that the program I is predicted to be the least preferred for user U, thus placed at the end of. So rank UI and RUI and CUI and PUI, pretty close variables at the end of the list. We opted for using percentile ranks rather than absolute ranks in order to make our discussion general and independent of the number of the programs. All good. Our basic quality measure is the expected percentile ranking of a watching unit in the test period, which is rank bar is RUIT. Why should we multiply? It doesn't make sense. Oh, rank bar is the over U and I. Alright, perfect. Among all. Oh. Okay. So rank bar is independent of U, independent of I. It's just function of T. Okay, and it is a metric for the whole system, for your whole recommender system, how good it is working. If your rank bar is pretty low, it means that, yeah, the recommendations are interesting. Lower values of rank bar are more desirable as they indicate ranking actually watched shows closer to the top of the recommendation list. Notice that for random predictions, the expected value of rank UI is 50%, the middle of the sorted list. Thus, rank bar is always greater than 50%, indicating an algorithm no better than random. Oh, okay. If rank bar of a system is above 50%, it is no better than random. All right, this is a metric.
Evaluation results. We implemented our model with different number of factors, F, ranging from 10 to 200. In addition, we implemented two other competing models. The first model is sorting all shows based on their popularity, so that the top recommended.
Because you can compare your results with other models. Well, we don't know what is the best ranking, but we have three ideas and this one was better. I like it.
Shows are the most popular ones. This naive measure is surprisingly powerful, as crowds tend to heavily concentrate on few of the many thousands available shows. We take this as a baseline value. The second model is neighborhood-based, item, along the lines described in Sector 3.1. We explored many variants of this scheme, and found the following two decisions to yield best results. 1. Take all items as neighbors, not only a small subset of most similar items. 2. Use cosine similarity for measuring item similarity. Formally, for an item I, let us arrange within our I set membership symbol RM the RUI values associated with all M users. Then, Sig equals RTIRJ cricker JK.
What is RIR?
The predicted preference of user U for show I is PJ Sig Raj. As a expected percentile ranking, percent 18, 16, 14.
Figure 1, comparing factor model, the value of f, with popularity ranking and neighborhood models. What is a neighborhood model? Popularity ranking and neighborhood model. Okay. So, popularity, which one was popularity? Expected percentile ranking. Then we have neighborhood, and then we have factor. You can see that the latent variable model, pretty simple. First of all, once we increase f, the rank bar decreases, the metric decreases, which is obvious. You have more parameters to work with, better, but the other ones, well, they should not change with f, but the thing is that the latent variable model is better than the other ones. Figure 2, cumulative distribution function. Cumulative distribution functions of the probability that the show watched in the test set falls within the top X% of the recommended show. Top 3% of the popularity, neighborhood, factor, and watched. What is a watched? Previously watched. So it seems the latent variable model works really well.
Side remark, we would like to mention that we recommend very different settings for neighborhood-based techniques when applied to explicit feedback data. Figure 1 shows the measured values of rank with different number of factors, and also the results by the popularity ranking, cyan, horizontal line, and the neighborhood model, red, horizontal line. We can see that based only on popularity, we can achieve rank equals 16.46%, which is much lower than the rank equals 50% that would be achieved by a random predictor. However, a popularity-based predictor is clearly non-personalized and treats all users equally. The neighborhood-based method offers a significant improvement, rank equals 10.74%, achieved by personalizing recommendations. Even better results are obtained by our factor model, which offers a more principled approach to the problem. Results keep improving as number of factors increases, till reaching rank equals 8.35% for 200 factors.
And saturates.
Thus, we recommend working with the highest number of factors feasible within computational limitations. We further dig into the quality of recommendations by studying the cumulative distribution function of rank UI. Here, we concentrate on the model with 100 factors, and compare results to the popularity-based and the neighborhood-based techniques, as shown in Fig. 2. We ask the following: what is the distribution of percentiles for the shows that were actually watched in the test?
Distribution of percentile, that's such a difficult combination. Distribution is already numbers and percentiles.
Said.
I don't know.
If our model does well, all of the watched shows will have low percentiles. From the figure, we see that a watched show is in the top 1% of the recommendations from our model about 27% of the time. These results compare favorably to the neighborhood-based approach, and are much better than the baseline popularity-based model. Here we would like to comment that results get much better had we left all previously watched programs in the test set, without removing all user program events that already occurred in the training period.
Do you
Predicting
agree?
redash.
Fuck off.
Watching a
I'm
program
talking,
is much
bitch.
easier than predicting a first time.
Yo! I think Spotify is far less aggressive than YouTube or Instagram. It is. Like, I feel I have more control when I am on Spotify. like changing the music. Like I can plan to listen to this. I mean, it's always me, but like YouTube is much more addictive in the sense that you watch this video and there is recommendation for other videos, or you are in the short. Well, Spotify doesn't have the short option. And to be honest, when you listen to something, maybe just I'm not a good listener, but when you listen to something, you can still look at other. That's the point, because YouTube needs you to both listen and look at the shit, watch it. So it is two senses, but Spotify is just one. So it makes sense that it is less addictive.
Here we would like to comment that results get much better had we left all previously watched programs in the test set, without removing all user program events that already occurred in the training period. Predicting redash. Watching a program is much easier than predicting a first-time view of a program. This is shown by the black dotted line in the figure, which evaluates our algorithm when previously watched shows are not taken out of the test set. Although suggesting a previously watched show might not be very exciting, it does come useful. For example, our system informs users on which programs are running today that might interest them. Here, users are not looking to be surprised, but for being reminded not to miss a favorite show. The high predictive accuracy of retrieving previously watched shows comes handy for this task. We would also like to evaluate our decision to transform the raw observations, the RUI values, into distinct preference confidence pairs, PUI, CUI. Other possible models were studied as well. First, we consider a model which works directly on the given observations. Thus, our model, 3, is replaced with a factor model that strives to minimize XY min, RUI XTUE, 2 plus lambda 1 xk.
So how was the 3? It was pretty similar. Okay. Dude, right at the beginning I knew that it was this.
Thus, our model. Notice that this is a regularized version of the dense SVD algorithm, which is an established approach to collaborative filtering 18. Results without regularization, lambda 1 equals 0, were very poor and could not improve upon the popularity-based model. Better results are achieved when the model is regularized. Here, we used lambda 1 equals 500 for regularizing the model, which proved to deliver best recommendations. While results consistently outperform those of the popularity model.
I think the beauty of this is just that it gives you a structure. Yeah, you may say, oh, you tried different lambdas to find. But it is still better than just not knowing what your fucking objective function should be.
They were substantially poorer even than the neighborhood model. For example, for 50 factors we got rank equals 13.63%, while 100 factors yield rank equals 13.4%. This relatively low quality is not surprising, as earlier we argued that taking RUI as raw preferences is not sensible. Therefore, we also tried another model, which factorizes the derived binary preference values, resulting...
Motherfuckers, they are just playing with the objective function and whatever gives you a good result. You don't, sometimes it is beautiful. Okay, I like it because in their research they're saying, dude, we don't know what is the objective function. We optimize for an objective function Then we see the metric that we had. So they are not optimizing for the metric right away. Why? Because probably this is not a quadratic form objective, or optimizing for the main objective is difficult, computationally hard. So you choose an objective function that is not your main objective, but solving for that objective will lead into good results for your main objective. That's a smart idea.
XY X min, Pui X T U Y, 2 plus lambda 2 X K sub 2 plus X K 2. The model was regularized with lambda 2 equals 150.
Figure 3, analyzing, what is this? Expected percentile ranking increases when you increase the number of bins. What is bin? I don't know. Based on popularity, decreases, but when you have user watching time, it increases. Analyzing the performance of the factor model by segregating user shows based on different criteria. Oh, it makes it worse.
Results are indeed better than those of model 9, leading to rank equals 10.72% with 50 factors and rank equals 10.49% with 100 factors. This is slightly better than the results achieved with the neighborhood model. However, this is still materially inferior to our full model, which results in rank equals 8.93%, 8.56%. For 50 to 100 factors. This shows the importance of augmenting 10 with confidence levels as in 3. We now analyze the performance of the full model with 100 factors on different types of shows and users. Different shows receive significantly varying watching time in the training data. Some shows are popular and watched a lot, while others are barely watched. We split the positive observations in the test set into 15 equal bins. Based on increasing show popularity, we measured the performance of our model in each bin, ranging from bin 1, least popular shows, to bin 15, most popular shows. As Fig 3, blue line, shows, As Fig 3, blue line, shows, there is a big gap in the accuracy of our model, as it becomes much easier to predict popular programs, while it is increasingly difficult to predict watching a non-popular show. To some extent, the model prefers to stay with the safe recommendations of familiar shows, on which it gathered enough data and can analyze well. Interestingly, this effect is not carried over to partitioning users according to their watching time. Now, we split users into bins based on their overall watching time, see Fig 3, red line. Except for the first bin, which represents users with almost no watching history, the model performance is quite similar for all other user groups. This was somewhat unexpected, as our experience with explicit feedback datasets was that as we gather more information on users, prediction quality significantly increases. The possible explanation to why the model could not do much better for heavy watchers is that those largely represent heterogeneous accounts, where many different people are watching the same TV. Finally, we demonstrate the utility of our recommendation explanations. Explanations for recommendations are common for neighbor methods since the system can always return the nearest neighbors of the recommended item. However, there is no previous work discussing how to do explanations for matrix decomposition methods, which in our experience outperform the neighbor-based methods. Table 1 shows 3 recommended shows for one user in our study. Following the methods in section 5, we show the top 5 watched shows which explain the recommended show, shown in bold. These explanations make sense. The reality show So You Think You Can Dance is explained by other redash. Expected percentile ranking, percent. 40 35. 30. Ality shows, while Spider-Man is explained by other comic-related shows and Life in the ER is explained by medical documentaries. These common sense explanations help the user understand why certain shows are recommended, and are similar to explanations returned by neighbor methods. We also report the total percent of the recommendation accounted for by the top 5. In this case, the top 5 shows only explain between 35 and 40% of the recommendation, indicating that many other watched shows give input to the recommendations. 7. Discussion. In this work we studied collaborative filtering on datasets with implicit feedback, which is a very common situation. One of our main findings is that implicit user observations should be transformed into two paired magnitudes, preferences and confidence levels. In other words, for each user item pair, we derive from the input data an estimate to whether the user would like or dislike the item, preference, and couple this estimate with the confidence level. This preference-confidence partition has no parallel in the widely studied explicit feedback data sets, yet serves a key role in analyzing implicit feedback. We provide a latent factor algorithm that directly addresses the preference-confidence paradigm. Unlike explicit data sets, here the model should take all user item preferences as an input, including those which are not related to any input observation, thus hinting to a zero preference. This is crucial, as the given observations are inherently biased towards a positive preference, and thus do not reflect well the user profile. However, taking all user item values as an input to the model raises serious scalability issues. The number of all those pairs tends to significantly exceed the input size since a typical user would provide feedback. 357. Show popularity user watching time. 9/11 bin hashtag. 1315. So you think you can dance? haLf.
3 recommendations with explanation for a single user. In our study, each recommended show is recommended. Each recommended show is recommended. Each recommended show is recommended. That makes sense. Due to unique set of already watched shows by the users. So you think you can dance, haLf Kitchen? Okay, I don't know what. Judge Judy, Moment of Truth. Okay, Judge Judy and Moment of Truth sound similar. Hell's Kitchen. Don't forget the lyrics. Spider-Man, Batman, Superman, Pinky and the Brain, Power, yep. Life in the ER, where is emergency room? Adoption stories, Deliver Me. Baby Diaries, I Lost It. It's about abortion, is it? Bringing Home Baby. Alright, yeah, they are also related.
Only on a small
Just
fraction
even
of
through
the
title.
available items. We address this by exploiting the algebraic structure of the model, leading to an algorithm that scales linearly with the input size while addressing the full scope of user item pairs without resorting to any subsampling. An interesting feature of the algorithm is that it allows explaining the recommendations to the end user, which is a rarity among latent factor models. This is achieved by showing a surprising and hopefully insightful link into the well-known item-oriented neighborhood approach. The algorithm was implemented and tested as a part of a large-scale TV recommender system. Our design methodology strives to find a right balance between the unique properties of implicit feedback datasets and computational scalability. We are currently exploring modifications with the potential to improve accuracy at the expense of increasing computational complexity. As an example, in our model we decided to treat all user item pairs associated with a zero preference with the same uniform confidence level.
So where are they? Game design. That's good. I missed them. Guys, let's go learn machine learning.
Since the vast majority of pairs is associated with a zero preference, this decision saved a lot of computational effort. However, a more careful analysis would split those zero values into different confidence levels, perhaps based on availability of the item. In our television recommender example, the fact that a user did not watch a program might mean that the user was not aware of the show, it is on an unusual channel or time of day, or that there is another favorite show on concurrently, or that the user is simply not interested. Each of these correspond to different scenarios, and each might warrant a distinctive confidence level in the no preference assumption. This leads us to another possible extension of the model, adding a dynamic time variable addressing the tendency of a user to watch TV on certain times. Likewise, we would like to model that certain program genres are more popular in different times of the day. This is part of an ongoing research, where the main challenge seems to be how to introduce an added flexibility into the model while maintaining its good computational scalability. Finally, we note that the standard training and test setup is designed to evaluate how well a model can predict future user behavior. However, this is not the purpose of a recommender system, which strives to point users to items that they might not have otherwise purchased or consumed. It is difficult to see how to evaluate that objective without using in-depth user study and surveying. In our example, we believe that by evaluating our methods by removing the...
Okay, that was a good paper, honestly. Now it's the time to just one round of counter. But really, you need to have a paper that you can read. Just any paper above 10 pages is bullshit. Papers below 10 pages are also bullshit, but they can at least be read. And then maybe once you have a paper below 10 page, you can read it and you can get the idea and implement it. That's all I'm saying. One round, dude. One field.
Let's roll.
I think all of them are like bots right now. Oh, it doesn't sound like that. Where are you guys? Ah, no, come back. I think that's I died with a delay. Woohoo! I knew I was going to be nice. I heard him. Damn, I killed you. How? Oh, fuck. There are guys there? Yeah, let's go. Dude, 2 times that. Fuck you, bitch. 3 times. He killed me 3 times. Who are you shooting at? Okay. These motherfuckers are so strong. Look. This line should be always for us, not for them. Knifed? Alright, let's go. What's the time? One round. Not 3 round, 1 round. Why? Why am I? Haha, I killed him. Ah, fuck! Killed me again. Ah. These guys are fucking destroyed. They're gonna kill me. Which was me? Who is shooting? Ah, what about that bitch? Don't come. Ah, let's go. Damn, this fucking vortex guy. Ah, bitch. Telling you one more there. Ah. Dude, it's just about the gun. And, or it's quartet. Who is shooting at us? Fucking. Ah! What can kill me? I kill. Fucking bot is killing me. What's this shit? I don't know why machine gun is good. When to use machine gun. That's, you know, you have the biggest gun and it's only good if you are at the closest. What is happening here? Dude, bot should not be able to kill me. Go, brother. Hello. They're going to knife me now. Bitch. Wow. Dude, bots are so strong. What happened? Don't get knife. Ah, okay, fuck this. Let's go, let's leave. Dude, this is not healthy. Okay, I'm playing too much counter. It's too unhealthy. Guys, I don't wanna play more than 15 minutes. 15 minutes a day. Alright? 2.5. 2.5 round. Perfecto. Good night.